said in the last class, in today's lecture and in the next couple of lectures, we focus on the fundamentals. Okay, we will focus on the fundamentals and get them cleared. Right? Uh, so while as we focus on the fundamentals, no, the problems, I will keep posting the problems, programming problems. You keep trying to solve them. Don't worry, again, want to insist, don't worry about OG or any of those things. Take the problem, understand the problem, uh, uh, give the appropriate input as you see fit, come up with the logic and print the output, and you try it out on few test cases. If it is working, it is good. Okay, that is the expectation from you. One out of three problems, but whenever you have time or enthusiasm, you can attempt to do more than one problem every day. But the general expectation is no, in a week or so, you should be able to solve moderate level problems comfortably. That is the goal. And by the time we come towards the last week, you should be able to solve even problems of higher complexity. That's the goal. So now let's get back to the fundamentals. So if you take, because so far you have written many programs. So if you take any program, if you take any problem, so the first part of it involves the problem or the program for the problem. It involves data. Okay, so what is the data uh, on which we have to process, which we have to act upon? So there is a data and then computations on data. Data and computations on data. So given you are looking at so many problems, right? So in every problem, you have to see what is the data you have to consume and how do you represent that data internally, and how do you represent that data internally. And then once you have that data model in your mind, then the next part is how do we go about computations on the data. So for example, if you think of your C programs, so because of this, if you see your C program, so at the beginning of your C program, you will see variable declarations. And these variable declarations, they tell you, so what kind of data you are working with and how do you want to represent that data. Like, let's say if you are working with student records, how do you store your student records? Okay, what data structure to use, you use to store your student records? Should you use an integer data type for the roll number, or should you use a floating point data type to store the roll number of a student? So on and so forth. All these questions come up. And then followed by the computations. This is your computations. This is the place where you write your actual compute statement. Similarly, if you see any function, so any function, like if you take a function has some parameters, and so if you see a function, it has some parameters. These parameters will tell you what is the data that is being passed to the function and what is its type. And then there is return type. Return type of the function. And then within function, again, there is this thing. So what is the data this function is working with? So you will have variable or data declarations. And then you have computations again. All right. So now if we look at the data, if you look at the data, so let's see. If you focus on, yeah, let's take a look at the compute model that we have. So so you have our yeah, your processor or CPU, and then we have the main memory, which is a linear array of bytes. Okay, so this is byte 0, this is byte 1, this is byte 2. So this is called as random access memory or main memory or whatever you have. And your CPU interacts with the RAM, and then you have your hard disk on which your a.out, the executable file will be present. And when you give your program for execution at the command prompt, then what happens is the instructions and data associated with this executable file will be loaded into the memory, and your processor starts executing. And if you look at each byte here, it's an array of bits. So this is, if you see, uh, so this is, so 1 0 1 1 0 1 1 1, for example. So each byte, it can hold an array of bits. So your whole memory, it's a linear array of bytes, and each byte, it is a sequence of 8 bits. It's a sequence of 8 bits. So if I ask you, what is present at byte 1, will you be able to tell what is present at byte 1? So even before I ask this question, anything that you want to work with, whatever you want to work with, whatever the data that you would like to work with, finally it has to be stored as a sequence of bits, because that is the only representation mechanism, hardware representation mechanism that we have. So it has to be mapped to bits, right? So given this, my question is, let's say if I show you, hey, these are the bits present in byte 1, in the memory location associated with byte 1, what does it represent? So if I ask you that question, will you be able to say anything? What would be your answer? Can you say anything about it? You can't comment. Yeah. So the reason is the bits by themselves, they don't say anything to us. They don't convey anything to us. But we have unless we have a mental map of what those bits represent, we cannot say anything about what those bits, the semantics of those bits. First of all, byte 1 could be corresponding to the operating system kernel or your program. Even if it is in your program, it could be corresponding to an instruction, or it could be present on the stack, or it could be present on the heap. All these things are possible. Let's say even if we know that this corresponds to some data in your program, will you be able to say anything about this? We say this particular byte number 1, it corresponds to some data in your program. Will even then, will you be able to say anything about what this byte represents? So we will not be able to say even then, just by looking at the bits, what is the semantics of this 8-bit sequence or the byte. Like for example, on my forehead, so you're all seeing me on webcam, on my forehead, I will write a 8-bit pattern on my forehead and ask you, hey, can you tell me what this 8-bit pattern corresponds to? Uh, yeah, so you don't know what that 8-bit pattern corresponds to. That 8-bit pattern could be representing my age. It could be representing my weight, or it could be representing my weight in pounds, or it could be representing my weight in kgs, or it could be representing no uh, uh, my body temperature, or whatever it is, right? So uh, the what a bit pattern by itself doesn't mean anything. We give semantics to it. We give semantics to it, right? So in order to illustrate this point that we have seen, for example, I think in one of the classes, I'm not sure whether it is in this section or in the other section, we wrote a code to print all the characters from A to Z. The code looks something like this. The code looks something like for C is equal to C less than or equal to Z plus C. And then within here, we have a very simple statement, printf %d %c. And then in order to have a nice, we have slash n c c c, right? So we wrote this code, and the interesting thing here is there are from your from our perspective, C is holding a character. This is ours. This is the programmer. This is the programmer perspective. So C is holding characters. This is the domain of alphabets. Okay, so this is the domain of alphabets. Um, so here, no, we are working with A, B, C, D. This is our view of the data that is present in the variable C. Yes or no? From our view, the data that is present in the variable C is this alphabet A, B, C, D. So it's a character, and it holds 1 byte. A character is allocated 1 byte. So that's our domain. But internally, but we know that these alphabets are represented using their associated ASCII values. Like for example, the ASCII value of A is 97, the ASCII value of B is 98, and so on and so forth. This is the domain of ASCII values. But then these decimal numbers, 98, 99, so on and so forth, they cannot be stored in that particular form in the computer. So in the computer, in the memory, this is this is your computer or memory. So the associated bit pattern will be represented 0110, 1110, something like this. So this could be the bit pattern corresponding to 97, so on and so forth. Right? So here, what is one interesting thing that is happening here is the same bit pattern. We can either think of it, you can interpret it as an integer and print. No, we are using %d to print, right? So the same value C 97, let's say C contains 97, the same value when we interpret it as an integer, it gets printed as an integer 97 on the screen. And if it gets interpreted as a character, it gets the associated character A will be printed on the screen. And then the next important thing is when we are doing ++C, what is this arithmetic on characters? No, what do you mean by incrementing the alphabet A or B or C? It doesn't make sense, right? But then this increment is happening in this in the space of the associated numeric code. That is 97 gets incremented to 98, and then when we interpret 98 as a character, we get right. So that's what happens. So the ASCII value of A 97 gets stored in C, and you kind of you print 97 uh, because when we interpret it as a number, and then you print character A when you interpret it as a character. you go to the end of the loop, you increment plus plus c, that 97 becomes 98. You check if 98 is less than or equal to the ASCII value associated with z. It turns out to be true. So again, you come here, you interpret 98 as an integer, and then you interpret 98 as an alphabet. Because of that, 98 followed by that corresponding alphabet gets printed. So the important idea here is, if you take a bit pattern, by that bit pattern by itself uh, doesn't have any meaning by itself. It's the semantics that we give to that bit pattern that matters. And as programmers, this mental map of the semantics of the different data entities that we are using, it should be very clear to us. Are you all with me here? Does this make sense? So later on, tomorrow in the next class, maybe I will talk. So like, for example, if you have something like char c is equal to a, and then if you have some integer n, and then if you say n is equal to c, then what happens is the ASCII value associated with the ASCII value associated with A, it gets copied into N, and now we just treat that 97 as an integer. But on the contrary, so let's say if you do instead the opposite, C is equal to n is equal to some 12, and then we say c is equal to n, then again the same copy operation happens, except that there is a problem that the integer n is allocated 4 bytes of memory. So we will discuss this in a while, but your character c, it has only one byte of this is your n and this is your c, and so only the least significant byte will be copied to the memory location associated with c. So all these bits, let's say if there is some value present here, some value present here, they will just be dropped, and only whatever the value that is present here, it gets copied into c. In some cases, no, that could be logically correct. In some other cases, logically, it could lead to wrong answers. But as programmers, it is our job to see that this makes logical sense. So this part I will talk in a moment, maybe in tomorrow's lecture one more time. But now let's go ahead and see, we will look at what are called as primitive data types. Okay, so primitive data types. So if you look at C, so we have integers, support to represent integers. So, integers, we use this keyword int, but so we can classify integers. There are two kinds of integers possible: signed, which is by default, all integers are signed, or unsigned. And then within that, we have long integers, and then there are default sized integers. When we just use int, that is default size, and short. Similarly, in unsigned also, we have the same. So these are the, so this is the primitive data types that are available in C to support to store data of type integers. And then we have, in order to store real numbers, we cannot store real numbers as it is, but we have data types such as float, double, long double, etc. And then we have char, and then underscore underscore bool. This is a new data type present in C99. And in some of the programs, we have seen a data type called as bool. Actually, bool is a user-defined data type, and that user-defined data type is present in std bool.h. So in the next class, I will talk about type def statement. So while these are the primitive data types, it is possible for us to define new data types by using what is called as a type def statement. So we can say type def underscore underscore bool. So now a new data type called as bool, it got created, and we can use it in our programs. And how is it defined? It is defined underscore underscore is bool is nothing but bool. This is a very simple definition here. And this particular statement could be present in stdbool.h. All right. So here, these integers and real numbers, so these are numeric data types. These are numeric data types. So when you are dealing with numbers, integers or real numbers, you have to work with. Are you all with me here so far? So any programming language that you look at, C, C++, Java, it doesn't matter. One of the things that you should be looking for is what are the primitive data types supported by this language. And from these primitive data types, we compose new data types. Like for example, an array of integers or an array of floating point numbers, or a structure which consists of two fields. One field is a character array, and the second field is no is a integer. And you can have an array of structures. So like that, what we can do is from these primitive data types, we can compose or come up with different new data types. So if you look at any programming language, so two things are important. One is the primitive data types plus a method for composing new data types. So this is important for you to understand. Yeah. Forget about that numeric part. So are you all with me so far on this? We are all on the same page. Does it make sense? Happy? Great. So now let's take a look at some code. Are you able to see the screen? The new screen? Okay, great. So here we have written a small program to which prints the size of the number of bytes allocated to different data types. Like for example, let's compile this program. So gcc types.h, control L. So you can see that whether it is an unsigned short int or a signed short int, the 2 bytes are allocated. Similarly, for integer, 4 bytes are allocated, whether it is unsigned or signed. Similarly, for long int, the 8 bytes are allocated, whether it is signed or unsigned. And for float, usually for float, 8 bytes are allocated. For yeah, I think for float, 4 bytes are allocated. Yeah, for float, for if a variable is of type 4 bytes are allocated, for double 8 bytes, and for long double 16 bytes are allocated. And for char, of course, 1 byte is allocated. For char, 1 byte is allocated. Right? So now when we say, yeah, let's see here. Here. Let me. So now let's think of a short variable, a variable short, and a short int. Short int is is allocated 2 bytes. So if you look at its representation, it is 16 bits. Short int is 16 bits. This is bit 0, on and so forth. 16 bits. This is bit 15. This is what is called as a least significant bit, LSB, least significant bit, and this is MSB, most significant bit. So this 16 bits can be logically divided into 2 bytes. First byte is bits B0, B0 to B7, and the second byte is bits B8 to B15, and we can call this as B1. This is B0. This is least significant byte. This is most significant byte. So in this particular case, they are next to each other. But let's say if you are working with a with a long int, if it's a long int, then you will have least significant byte is B0 and the most significant byte is B7. And there are 8 such bytes and each byte holds 8 bits. So overall 64 bits are allocated to a long int. In terms of memory, when we say that a particular short int is allocated memory at the location 4, then what it means is, this is location 4, then what it means is bit B0 will, byte B0 will be present here and byte B1 will be present here. This is how a 2 byte short int will be laid out as a sequence of bytes in the memory. Similarly, when we say the address of some long int variable, a long int variable starts at address 16, then then that means B0 is stored here, so on and so forth, till this is B7, 16 plus 8 is 24, 23. Yeah. So bytes 16 to 23, they hold this entire 8-bit long integer. Does this make sense? You're all good? Any questions here? Any questions you would like to ask me? I'll take a pause and you can ask any questions you have. Anjali? You're doing all right? Anjali, Anish, Ananya? No, so the idea of positive and negative numbers, Vitish, I will explain in the next class. Okay, hold on to that. Good question. I'll explain in the next class. See, Ananya is the one who wants to make us all listen to some music during the lab exam, no? Okay. Good, good. What really helped? Music. Huh? Nice, nice. You all thank Ananya. Otherwise, if I put music, I start focusing on the music. Okay, okay. I cannot work, yeah, with music. Same. Anyway, so whatever works for you. Good, good. Okay, so now, um, so you put that in Discord and all here. How does it work? Or you have a group? Okay, anyway, let me not get into those details, but yeah, have fun. You should enjoy what you are doing, is including exam. Okay. So now let me. So there is one interesting question that is asked in the other section, which I would pose here. That is, with let's go back here to the code. So here, so C provides data types, short int, int, long int, and so you can. So if the size of the data you are working with is less than, no, it can hold within 2 bytes. You use short int. But if it requires greater than 2 bytes, but less than 4 bytes, then you use the data type int. And finally, if it even 4 bytes are not sufficient, then you may have to go to long int. So my question for you is it necessary? Do you see any use cases where we may be working with integers which require greater than 8 bytes of memory? Is there any use case where you think practically speaking, where the number of bytes required is greater than the amount of memory required is greater than 8 bytes? Factorial of a big number. I'm talking about integers. Okay. Why do you think LCM? I want to see, if you generally want to say I want LCM of some 2 power 30, no 94 and no 2 power 94 plus whatever something, then you can always find the necessity for large numbers. Like for example, when you multiply really two big integers, or when you try to find factorial, but in practice, do you require uh, do you find do you encounter cases where the integer values that you encounter, they cannot be fit in 8 bytes? Nikhil says distance between stars or speed calculation. Then we use Nikhil, we use float or double or long double. We don't use integers. Okay, Vidhi, and Vidhi says a number with 1,000 or more digits and we want to count number of digits. Tell me, apart from the programming course, do you really find a case where you want to count the number of no digits in a number with more than 1,000? Factorials, finding large primes, yeah, good, good. So now, no, RSA, yeah, cryptography, nice. Yeah, so in cryptography, like like later on you will learn public key cryptography, private key cryptography. So there you will be working with large numbers, like 128 bits, 256 bits, 1024 bits, 2048 bits, like that, you will be working with encryption algorithms involving that large number of bits. So then what do we do? Okay, so we will long int is not available, is not sufficient, because using long int we can only hold 64 bits. What should we do? How do we solve this problem? So if not available, we have to make ints of our that size. How do we make that, Rahul? Use struct, make a struct. Good, good. Don't we have long, long, long int, long, 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 long int? Vitish, brilliant, man. Uint underscore underscore 128. Okay. Define an array. Great, that is one option. Okay, so good. So structs, um, uh, good, good. Rahul has got it. So use array, so is one option. Okay. So here, yeah, so pay attention to this program. So in this program, so let me actually Control A, Control C, Control N. So let's say, let me make it simple, and then I'll keep adding stuff to this code. So let's say if you have, you are working with short integers. So short int, you know, it's a, uh, uh, yeah, it requires 2 bytes, and your program, your particular problem you are solving, you requires only short ints. The data size is small, so you can declare some variables as short ints, and then when you want to perform arithmetic on them, you can use the available operators given by the C programming language. Right? So one important thing is on the primitive data types that you have, like short int, long int, or double, float, etc., the associated arithmetic operators like addition, subtraction, multiplication, they are already provided to you by that as by default. So, like for example, here instead of if you are working with a regular sized integer, or let's say if you are working with long int, so you have long int, so, and then you can say ln3 is equal to ln1 plus ln2. So what happens is these for the primitive data types, a set of associated operations are already, operators are already defined, and we can use those operators: addition, subtraction, multiplication, remainder, things like that. But let's say if you want to know whether, if you want to compute the square root of a integer, okay, and round it off to the nearest integer, then there are two possibilities. One possibility is that operator is not available, but you can rely possibly on the math library of the C, and the math library may have a solution for it. But for some things, the math library may have a solution. For some other things, the math library may not have a solution, in which case you have to write your own function. Like for example, you want to check if a given number is a prime or not. The math library may not have that primality checking function, so you have to write your own function. And one more interesting thing is, let's say you have a floating point. Fn3 is equal to Fn1 plus Fn2. So here, if you see, we are using the same add operator to add short integers, long integers, float numbers, etc. But the addition, the underlying algorithm to add two floating point numbers is very different from the underlying algorithm you use to add two integers, short integers or long integers. But all these things are automatically taken for you by the compiler. The compiler knows that you are trying to add floating point numbers, and it invokes an appropriate, maps it to an appropriate floating point addition instruction from the processor. And when it sees that you are trying to add two integers, depending upon the size of the data, again it maps it to appropriate instruction from the processor instruction set architecture. So this is all good, but the problem comes like as let's say if you are working with, you want to work with 512-bit numbers, you are working on some cryptographic algorithms, and you are working with some 512-bit numbers, then what happens is no, you end up declaring an array like this, an array of 8 unsigned long ints. So every unsigned long int is of length 8 bytes, and every byte is 8 bits. So how many bits you get? So overall you get 512 bits. Okay. So how is this? So the size of the array is the size of the array, 8 elements. If you see this, I'm talking about this. So it has 8 elements and 8 bytes each. Each element is of 8 bytes, and then each byte is of 8 bits. So overall, the number of bits is 8 times 8 times 8. That is no 2 cube. 8 is 2 cube, 2 cube, 2 cube. When we add all those things, multiply all those things, you get 2 power 9. 2 power 10 is 1024. 2 power 9 is 512. So what happens is in the memory, the whole, if you see in the memory, this is your memory. In the memory, what happens is, so this is your key 1 of 0, and the next is key 1 of 1. So you will see an array of 8 elements in the memory, but within an element you will see, no, this is so this is byte 0, this is byte 1, so on and so forth. So overall you will see an array of 64 bytes in the memory. Are you all with me here? How you are representing a 512 byte number, 512 bit number in the memory? Yes or no? So now, yeah, so it's representing is great, but the question though is, what's the question? If you want to add two 512-bit numbers, if we go ahead and write key 1 is key 3 is equal to key 1 plus key 2, it's not going to work. The C compiler doesn't recognize this as no 512-bit numbers. So when we want to perform addition operations on these 512-bit numbers, then you are on your own. Okay. So you may have to write a function. So you may have to call a function, add 512, and say key 3, key 1, key 2. So you have to write a function like this. Yeah, so this is the, so let me use D for destination. This is destination, source 1 and source 2. Now, how do we add to these two numbers? Do you know the algorithm to add these two numbers, to add the source 1 and source 2 and store it in destination? Do you know the algorithm? Yes, no? So here you need to know how binary arithmetic works, and I will explain a little bit of binary arithmetic in the next class. So if you know how binary arithmetic works, then you just have to apply that algorithm to write this function. Are you with me here? The how to add these two 512-bit numbers, it's a challenge. So we have to figure that out. But it is very similar to what you do when you try to add two numbers. Let's say, for example, when you want to add, let's go back. Yeah, if you want to add 21 and 49, so what happens? 9 plus 1 is 10. So you put 1 here and 0 here, and you'll say, what is this one? This is 1 is this 110. You put 110 here, you put 110 here. 6 plus 6 tens plus 110 is 7 tens, 70. In the binary system, you have 1 0 means this value is 2 power 0, this value is 2 power 1. And so let's say if you are trying to add one, the last part, this part, don't worry about it, I'll explain again, but I want to give a quick idea. So 0 1. So when you add 1 and 1, uh, so this 1 represents this is equal to 3. This whole 1 1 is equal to 3, and this is equal to 1. And when you add these two, what happens is 1 2 comes here and 0 will remain here. 1 plus 1 is 1. So 1 2, this is 1 1 2 comes here, and 1 2 plus another 2 is 2 2's. Okay, but so how do we do 2 2's? So it will 2 2's is nothing but 4. So we kind of write it as 100. Anyway, so this last part, ignore it, guys. Don't worry about it. But because I will cover it again in detail in the next class. But what I want you to understand is when we are working with so we have these primitive data types. We can work this with these primitive data types, and there are operators on these primitive data types. As long as the computations on primitive data types involve only these operators, we are good. But if we have to do something more complex, can use a library, or we have to write our own functions as operators. That's number one. Number two is if you are working with data, so which doesn't quite uh, cannot be captured using primitive data types, we have to create our own data types. And when we create our own data types, we have to define our own operators on these data types. Does this make sense, guys? Are you with me? The summary of today's lecture. Leaving aside the last part on the binary arithmetic. Ask me, Kesho. It's not clear. What is not clear? Tell me. Or did you say no for the binary arithmetic question? Okay, okay, got it here. So does this all make sense, today's lecture? You're all with me in this today's lecture? So in the next 2-3 lectures, we will go in a similar fashion covering the foundations. And as I cover the foundations, you please keep trying the problems that are posted. Don't wait for OG or anything. Solve the problems, have your own input, and then solve them, and check if it is all few test cases you can write and test, check if it's all looking good. Okay. So I will stop here. I'm planning to take the first 1 hour of tomorrow's lab session.